What are the 10 universal quantum truths that we know to be true? The realization that the macroscopic, classical principles that regulate electricity, magnetism, and light do not necessarily apply to the subatomic scales provided mankind with a new perspective on the universe. This discovery opened the door for the development of quantum mechanics. This quantum picture is larger and more all-encompassing than the majority of individuals, even many specialists, are able to comprehend. The following list of 11 fundamentals of quantum physics may inspire you to rethink your understanding of our universe on the lowest scales and beyond after you read them. Have a look at these 10 truths about quantum physics about our universe. However, before we start our countdown, we would appreciate it if you would subscribe to our YouTube channel and also press the bell icon. Let's get started. 10 Schrödinger's cat is either dead or alive, not both. To begin this list of quantum truths about our universe, keep in mind that the quantum function of macroscopic things decays extraordinarily quickly. This fact, which was not widely recognized in the early days of quantum mechanics, will serve as a good place to start. This decoherence is brought on by repeated encounters with the environment, which are difficult to avoid in surroundings that are relatively heated and closed off, such as those that are essential for life. This suggests that what we consider to be measurement does not require the presence of a person. Rather, the act of interacting with one's surroundings is sufficient to qualify as measurement. This helps to explain why it is so difficult to place large items in a superposition of two distinct states, as well as why the superposition loses its strength so quickly. A carbon-60 molecule is the heaviest item that has been placed into a superposition of positions so far. Nevertheless, some of the more arrogant people have urged performing this test on viruses or even heavier organisms like bacteria. As a result, the paradox that was brought to light by Schrödinger's cat, the transfer of a quantum superposition from a small thing, the disintegrating atom, to a large object, the cat, has been resolved. We now know that whereas very little things, like atoms, can remain in a state of superposition for extended periods of time, a much larger entity will very immediately become fixed in one state. Because of this, we never come across cats that are either alive or dead at the same time. 9 Wave is particle and particle is wave. According to quantum physics, every single particle is also a wave, and every single wave is also a particle. The conclusions of quantum mechanics are made abundantly obvious when one observes a particle at distances that are similar to the wavelength associated with it. As a consequence of this, atomic and subatomic physics cannot be understood without quantum mechanics, despite the fact that quantum action has no influence on the orbits of planetary bodies. 8 Quantum impacts are not necessarily small. We rarely observe quantum effects across considerable distances because the essential correlations are so feeble. Quantum effects can, however, endure for a significant amount of time provided that they are handled with the utmost care. Photons, for example, have been shown to get entangled despite the fact that they are separated by hundreds of kilometers. Bose-Einstein condensates are a degenerate form of matter that may be created at extremely low temperatures. In these condensates, up to 1 million atoms can be induced into a single coherent quantum state. Last but not least, there is a school of thought among certain physicists that suggests dark matter might have quantum consequences that go beyond individual galaxies. 7 It's all about uncertainty. Quantum mechanics is predicated on the idea that there are observable pairings that cannot be measured simultaneously, such as the location and momentum of a particle. This is the fundamental assumption of the field. The difficulty to properly measure both of their values is what differentiates a quantized theory from a non-quantized one. This is one of the quantum truths about our universe. It is not due to any shortcomings in the experiments that this hypothesis is necessary in quantum mechanics. One of the most odd manifestations of this is the uncertainty of energy and time, which according to Einstein's E=mc2 formula suggests that unstable particles have masses that are intrinsically unpredictability. 6 Einstein didn't disprove it. Einstein was not a skeptic of quantum physics, despite the widespread perception to the contrary. It was impossible for him to be correct because the idea was first so successful that a real expert would be unable to dismiss it. He won the Nobel Prize for his discovery of the photoelectric effect, which revealed that photons operated both as particles and waves. This finding is considered to be one of the most important discoveries in the field of quantum mechanics. Instead, Einstein contended that the theory was insufficient and that the inherent unpredictability of quantum occurrences required a fundamental explanation. He believed that this explanation might be found in quantum mechanics. He did not consider the randomness to be problematic, rather, he believed that this was not the conclusion of the story. An outstanding explanation of Einstein's thoughts on quantum mechanics may be found in the essay What Einstein Thought About Quantum Mechanics written by George Musser, which I highly recommend. 5. Quantum physics, an intense research field. Almost a century has passed since the hypothesis was first proposed. Nevertheless, many of its points of view are only put to the test when current technology are applied. Quantum optics, quantum computing, quantum thermodynamics, quantum cryptography, quantum information, and quantum metrology are all relatively new areas of research that are undergoing rapid expansion. The new knowledge that may be obtained through the use of these technologies has sparked a revival of interest in the theoretical underpinnings of quantum mechanics. 4. There is no weird action at a distance. In quantum physics, information is never transmitted non-locally, which means that it never skips across a certain distance in space without first traveling through all of the locations in between. Entanglement is a non-local phenomenon in and of itself, but it does not carry out any action. Rather, it is merely an association that is unrelated to any non-local change of information or any other apparent change. When you fully comprehend a study in which two entangled photons are separated by a large distance and the spin of each one is recorded, you will realize that no information can be transmitted faster than the speed of light. In point of fact, if you try to combine the findings of two separate observations, the data can move no faster than the speed of light, and in no case can they move any slower. In the early days of quantum mechanics, the concept of information was the subject of significant debate. However, we now know that the theory can be fully matched with Einstein's theory of special relativity, which states that data cannot be moved faster than the speed of light. This finding supports the theory that information cannot be moved faster than the speed of light. This is one of the most fundamental aspects of quantum physics that pertains to our universe. 3. Entanglement, not the identical as superposition. The ability of a system to exist in two distinct states at the same time is referred to as a quantum superposition. However, when a system is measured, one only ever discovers a single state and never a superposition. On the other hand, entanglement refers to a relationship that exists between two or more parts of a system and is considered to be something entirely separate. There is nothing fundamental about superpositions. Rather, whether or not a state is a superposition is determined by what you are trying to measure. For example, a state could be in a superposition of locations, but it couldn't be in a superposition of moments. As a result, the meaning of the term as a whole is somewhat ambiguous. Entanglement, on the other hand, cannot be misunderstood. Not only is it a fundamental characteristic of all systems, but it is also the most well-known measure of the quantumness of a system. 2. Quantization doesn't surely imply discreteness. Quanta are discrete particles, according to the dictionary definition. However, not everything chunks up or becomes separate as the scale gets smaller. Because electromagnetic waves are composed of quanta that are referred to as photons, it is possible to think of the waves as being discretized. This is one of the quantum realities that pertain to our universe. In addition, the electron shells that surround the nucleus of an atom can only ever have definite and distinct radii. On the other hand, other particle properties do not become discrete even when a quantum theory is applied. For example, the state of electrons in the conducting band of a metal is not discrete. Rather, an electron in the conducting band may occupy any continuous point within the band. 1. All is quantum. We now understand that certain objects are quantum mechanical while others are not. The only difference is that the quantum effects of large things are hard to detect. Everything else in the universe is subject to the same laws of quantum physics. It was not until scientists needed to explain why electrons reside on shells surrounding the atomic nucleus that quantum mechanics became necessary for making correct predictions. This is why quantum mechanics was a latecomer to the development of theoretical physics. So, that's it for today. We hope you enjoy the video. Tell us what you think about the video in the comments section below. Also, make sure to subscribe to our channel and click the bell button to get all the latest updates.